Today's webinar is part of the BHS webinar series, Future Hydrology in a Changing Environment. I'm really pleased to welcome you all here today to this webinar. Our president, Nick Chappell, would usually be doing the introductions, but he is caught up with field work that he's been able to do today. So as BHS Honorary Secretary, I would like to welcome you to the webinar. And this series was set up by Mike Cranston, who was our BHS Honorary Secretary until last month. Today's webinar is given by Chris White from the University of Strathclyde. And he is the Director of Postgraduate Research and the Head of Water, Environment, Sustainability and Public Health in the Department of Civil and Environmental Engineering. And he specialises in understanding and modelling and predicting extreme weather events at the sub-seasonal to seasonal and also the climate timescales. And today's webinar will focus on the recent progress made in hydrological forecasting across these different timescales, and will explore the future potential of hydrological forecasting.
Thank you very much. Thanks very much for the introduction, and it's a pleasure to be here with you all this morning and see such a large number of participants being involved. Thank you. So after the introduction, so that the title, Future of Hydrological Forecasting, I think Mike Cranston said soon after I gave him the title, he said, well, you'll be sure to get a good number of participants tuning in to listen to a talk with that sort of nice generalized title. So hopefully I can match some of that expectation with actually some content. So I'm Chris White. I'm University of Strathclyde, as was introduced. I'll touch on just some of my background a little bit more as I go into the talk, but just want to acknowledge several of the people that have either actively or without knowing it have contributed to some of the information and the slides that are contained in here. Obviously reference back to these people, but I'd like to just acknowledge those people that have all helped as I was putting together this talk. Okay, so today's subject, a very wide-ranging topic, future of hydrological forecasting. I'm just going to break down into, well, effectively two key components. The first one, I'll just do a little bit of background introductions to why I'm effectively talking to you today about ensemble and impact-based forecasting, but the majority of today's talk is going to be around this a vision or a potential future for collectively the topic of hydrological forecasting. So the majority will be on those two bits there of ensemble forecasting, impact-based forecasting. But just before obviously I go on to that, I should just do a little bit of a background introduction, because although I know several of you, many of you on here, I may be sort of I suppose a new quantity to some people. So I'll just give a slight touch of a background. So there's my, my face again, I'm sorry, but that's me. So I'm head of the Centre for Water, Environment, Sustainability and Public Health, which is a bit of a mouthful, I will grant you. I'm in the Department of Civil Environmental Engineering at Strathclyde, as was introduced. You might notice there are a few Australian components to this talk today, and that's because I spent 8-9 years or so in Australia, both at the University of Tasmania and the Bureau of Meteorology. So in many of the talks I still give, there's still work that comes through from there, either my work or of course other people's work that comes through. My areas are climate, risk assessment, compound events, but in particular, of course, with this bit here, I'm a hydrologist by background, and that sort of mix of hydrology and meteorology, and therefore a bit of a view towards the future for forecasting. Hydrological forecasting is, of course, the focus of where we are today. As a centre, the centre with a long name, we cover a range of topics, but the bit that I look after is particularly water, climate and natural hazards space. But we sort of branch out across environmental health, energy, circular economy and other topics as well. Why ensemble and impact-based forecasting? Why am I talking to you about this topic today? Well, my background kind of covers these kind of three sort of areas, I suppose. The years I spent working at the Bureau of Meteorology was ensemble forecasting, meteorological ensemble forecasting, and I'm still very active in that community from an application perspective. I've worked a lot with users, particularly in risk-based settings, so user workshops. Again, I'm afraid there's a photo of me in the middle there. That's the last one, I promise. As a hydrologist, I have done a lot of work, of course, in the hydrology space, but increasingly in the flood forecasting and impact-based forecasting space as well. So today's talk, therefore, is kind of pulling these threads together to form a narrative around this topic of the future of hydrological forecasting. But just before I get into this, I guess I'll say that whilst most of the information that's in here is information I've compiled, I talked to some of the projects that I've worked on or am working on, but of course there's also reference here to a lot of other people's work, and that's where those acknowledgements very much acknowledge those people whose work I'm referring to and commenting and referencing within this talk. So not everything, of course, I'm showing here is mine, but again, hopefully I'm sort of showing clearly where everyone's work is and how it fits into this as a topic. Just for those who may be new to the forecasting space, I'm of course aware that BHS has a wide remit, but in the forecasting sense, of course, what we're talking about here is the forecasting of hydrology. So whether that's for water resource use or you'll see in the talk I'm giving here, there's of course a clear focus, or there's clear orientation towards the flood side, so the hazard side of hydrological forecasting. So in a high-level sense, and this is from Rebecca Edmonton down in Reading, this is from a paper that she produced a few years ago, looking at, in a high-level sense, what would make this is for continental and global scale, and of course hydrological spans all scales, but in a nutshell, this image here describes pretty well the process of what we're talking about, which is hydrological forecasting, which of course involves some kind of meteorological input at the beginning, a numerical weather prediction model, which will produce a precipitation and other meteorological variables, which will then feed into a rainfall runoff component, a routing component, so a way of conveying the rainflow into river flows and then into something that then might create, say, a flood warning or forecasting of a flood that's due to occur. And then within there, of course, there are various other inputs, and there are several steps of processing. But as a very high level, this is kind of the process, irrespective of what time scale or what scale we're talking about. This is a good representation of what we're talking about here in terms of hydrological forecasting. Hydrological ensemble forecasting involves many, of course, of the same components as general hydrological forecasting is. It still needs those same meteorological and other inputs, whether that's soil moisture, runoff, and river flow. So it has that same process, of course, attached to it. And the output, again, is the same, whether that's for water resources or whether that's for flood and flood prediction and flood warnings. But with ensemble forecasting, the inputs are driven usually more by an ensemble, meteorological ensemble of plausible forecasts. So whether they're typically multi-member, and this slide here, dates back to 2009, which was a seminal paper. Hannah Cloak and Florian put together this a review of where ensemble flood forecasting was. That's back in 2009, but it's still used as a good, a perfect starting point for a talk like this, because this demonstrates what we're talking about here of a feeding of a meteorological ensemble. So multiple members driven by typically a large scale, often global scale, a meteorological model feeding into then a series of hydrological rainfall runoff scenarios. some of which may then produce, as you can see in this slide, some very high level warnings, but the majority of those members you can see in this example are below any perhaps level warnings. But the idea, of course, here is to reduce the uncertainty of what may or may not happen in a flood and what might happen in the catchment as a whole. So ensemble forecasting offers that possibility of more scenarios in which to reduce that uncertainty down and to get a better handle on what the prediction might be. And it's that basis, that basis of ensemble forecasting, so that meteorological input into hydrological models is the basic cause of EFAS. And EFAS is sort of the groundbreaking continental scale model, which uses ECNWS ensemble forecast to produce a series of ensemble forecasts for the large-scale basins, transboundary catchments that are across Europe. So anyone that is involved in hydrological forecasting, of course, will be probably quite familiar with EFAS and how that's developed over the last decade or so. Now, EFAS works on the basis of taking those ensemble forecasts from the meteorological component, doing some kind of pre-processing. Now, it depends on which perspective you're looking at here, whether you're looking at it from the meteorological side or from the hydrological side. From the hydrological side, that's pre-processing because it's going into the hydrological model, of course. But also, if you're then looking at it from the meteorological side, there'll be some kind of post-processing. So in other words, getting some kind of handle on what the outputs of those new ensembles mean before they will be entering into the hydrological model. And then increasingly, there's also, of course, a focus on the post-processing. So post-processing, again, from a hydrological model perspective, looking at how to interpret, in effect, those multiple members that will come out of a hydrological model before they will then go into some kind of a warning or a communication tool. And of course, EFAS here, part of its ethos is around how to communicate the warnings that will come from EFAS. Now, at that sort of scale, there aren't too many examples like that. The nearest I can think of to that is the Bureau of Meteorology in Australia. So there's kind of a bit of Australianism being brought into today's talk. So the Bureau of Meteorology, in a sort of similar way to EFAS, produces, in combination with CSIRO, of course, in Australia, it's 7-day ensemble stream flow forecasting. I've managed to condense the description of that into a few words on the right-hand side there, but they have a really good, very descriptive website as to how they produce these ensemble of streamflow forecasts based on the rainfall inputs. Now, although this is one country versus a European-wide continental scale ensemble forecasting product, of course, Australia being a large country, you can almost sort of say that's a sort of continental scale in itself in the way that it operates. However, of course, this is slightly different in that in this one, this isn't this is spread around more the gauged catchments across Australia. So if we're talking about ensemble forecasting, a lot of us will have been looking at hydrological forecasting very much from the hydrology perspective, but a little bit of the focus and I'm starting to look a little bit more to the future vision, I suppose, in some ways for hydrological forecasting. If we've got this ability already to produce 7-day forecasts based on ensembles, so based on meteorological ensembles, what's the next generation? Where are we going from here? So there are many ways you can look at this, but the focus that I'm looking at here is to pull on some of the work that I and of course many others have done in the past, which is around the meteorological input. So again, that argument of whether you're pre or post, this is the bit that is pre, this is the bit that is before it goes into the hydrological model. And meteorological ensemble forecasting is, of course, a meteorological a center-driven exercise. ECMWF is a good example, a prime example there of a meteorological center that produces ensemble forecasts. And there are about a 10 to a dozen or so of the big meteorological centers around the world that will produce models that are that range from weeks into months, so that's subseasonal into seasonal, or week, subseasonal and seasonal forecasting. And they all kind of follow, and this is a very generalized example here, but they all kind of follow this sort of similar approach of some sort of data assimilation, a coupled model of the atmosphere and ocean with a land surface model contained within there, from which, based on those initial conditions, are produced an ensemble of forecasts. And from a hydrologist's perspective, we then tend to come in, of course, at that endpoint, which is we take those ensemble forecasts and then need to do something with them and put them into hydrological models. Now, operational ensemble forecasting is its own branch. So from, again, a meteorological sense, these are also produced not just from a hydrological perspective or a usage perspective, but also just from a general communication perspective. So on the left-hand side, that's a plot from ECMWF, and the right-hand one, again, that's Bureau of Meteorology in Australia. But the right-hand one is slightly different, in that that's an El Nino La Nina forecast. So that's more to do with a climate driver, as opposed to the left-hand side, which is a temperature anomaly ensemble forecast. But the reason I'm showing this slide here is to, I guess, to demonstrate that ensemble forecasting, the inputs which go into a hydrological model, they extend, of course, beyond that. In other words, there's a science, there's a whole area, of course, of research and operational forecasting that produces these ensemble forecasts. And it's that community in itself that is, and has been for the last 5 to 10 years, is starting to piece together its capacity in terms of ensemble forecasting to bridge some of the gaps. And the gaps typically exist within a certain time frame. Seasonal outlooks, so if seasonal outlooks like those two plots I was just showing there, they can often be in weeks or month timescales. So seasonal outlooks will give an idea as to what's going to happen, say, with large-scale climate drivers over the next few weeks and the next couple of months. So the seasonal timescale. At the other end, we've got the weather forecasting timescale. Now, again, from a hydrology perspective, it's this weather forecasting timescale that we perhaps traditionally, as forecasting hydrologists, will be used to using. And definitely those two examples are just showing there of EFAS and the Bureau of Meteorology's streamflow forecasting. It's traditionally been more numerical weather prediction that has been feeding into, of course, our climate models. And then it's EFAS that starts to take that ensemble approach. And it's an ensemble approach. If we were to then try to put these two pieces together to say, well, if we're doing ensemble forecasting of shorter timescales, let's say up to about a week, which is in this kind of weather forecasting timescale, the gaps that exist, there's the gaps that exist between weather and seasonal, are starting to be filled by the meteorological community primarily, not completely, but primarily in this subseasonal timescale. And it's this subseasonal timescale, which is this kind of 10 to 30 day timescale, that from a meteorological ensemble forecasting community perspective has shown significant progress in the last 5 to 10 years. And it's that space that I've been working in very much from a use and an application perspective since around 2011, 2012 kind of time. Now, with those timescales, and again, I'm thinking generally here, but I'm also looking at this in regards to this talk very much from a hydrological forecasting perspective. But with the introduction of the potential of longer range timescales from ensemble forecasts, so again, just trying to move it on a bit from perhaps our typical 7-day forecasts, with those new timescales comes new challenges, but also potential new users and new user needs. So our subseasonal, again, just to clarify, we're talking sort of about the 10 to 30 day ahead, so beyond the typical weather forecasting timescale, but very much within a probabilistic range of plausible forecasts. We'll come on to scale, of course, a little bit in just a minute. But within those timescales, there are skillful forecasts if they are assessed and communicated correctly. So the challenge, therefore, is to how to use those sort of that new forecasting timescale. And part of that question can be answered by understanding what decisions are made within that timescale, and who those users would be. Now, from again, I'm putting this through the lens of a hydrologist and hydrological forecasting. The first one that would always come to mind would be perhaps on the humanitarian aid, so that preparedness, getting ready for something beyond the typical length of, say, a weather forecasting timescale. So if decisions can be made about, say, emergency management on a few days ahead to a week, if you had a reliable forecast of 1 week or 2 weeks or 3 weeks, from a humanitarian aid and support perspective, information there could, of course, feed into planning, allocation of resources, and that could also then feed into other things, such as water resources and agriculture, all of which all have a role to play in perhaps this overarching topic here of humanitarian aid. Perhaps a bit closer to home in terms of what we may be used to or would typically think of from a very much a water perspective, of course, will be energy generation. And I'm thinking here, of course, more about either directly through hydropower generation, which of course uses the water in our reservoirs and the rainfall to generate power, but also in a more general sense, from a meteorological forecasting side. Of course, wind forecasts will also govern the ability to generate energy from wind as well. So again, the ability to understand when we can't generate energy from weather in general, so taking it out of the hydrology space for a second. It's ensemble forecasting, and ensemble forecasting on perhaps the slightly longer timescales than we might traditionally be used to is perhaps offering an opportunity for scope and development over the next perhaps 10 to 20 years or so, as, and the intention is, of course, as sub-seasonal and seasonal ensemble forecasts become more and more skillful through higher resolution and of course, better representation of the physics of the atmosphere and what have you within those models themselves. A good example, and thanks to Elias for this slide, a good example of that push into those slightly longer timescales, now specifically here with respect to a hydrological forecasting perspective, the S2SV, so sub-seasonal to seasonal for energy project, which is a key member of that project. The example we've got here is looking at sub-seasonal and seasonal forecasts, but now for a particular application. In this case, it's for hydropower. This is an example here from 2015, which is a spring flood period, which is forced, again, using the ECMWF seasonal model, so ensemble model, but to generate outputs from those ensemble members to produce outlooks on those slightly longer timescales. And this S2SV, and I've tried to put through this talk, I've tried to put the links up here that you can, if you have access to these slides afterwards, you should be able to follow the links to each of these projects. This is quite a groundbreaking project we're looking at here, in that they're really pushing the boundaries of how to couple different disciplines together, how to couple, in this case, it's energy, with these more, with a newer generation of ensemble forecasts that again go beyond the length of perhaps our more traditional weather forecasting timescales. Now, sitting above that is a World Meteorological Organization prediction project, which again I've been involved with now since 2012. Now, my focus within here has always been in the application. So there's a whole subset now. I would say probably 80–90% of this project is around model physics, model development. In other words, how to improve the meteorological ensemble models to produce better forecasts. And that, let's say 10% or so, is actually, if we do have those better models, how can we use them? How can we apply them? How can they be used across disciplines? And again, I'm very much, of course, coming at this from a hydrologist perspective here. But this project, so it's now in its second phase, it's in second phase from a couple of years or so ago, is really trying to galvanize and build this community from the meteorological forecasting perspective. But equally, we can go to the hydrology side, and HEPEX, which I'm sure is an organization that many of you will be familiar with and will have had connections with. I'm sure there are HEPEX members that are sitting here listening to this today. The HEPEX community and projects that have been connected to it, such as the IMPREX project, are looking at the use, of course, of ensemble forecasting, but very much, of course, from the hydrology perspective. So part of my interest and part of my, I guess, focus of this talk here today is, of course, the bringing together of these hydrological and meteorological forecasting communities. We've of course we're effectively coming, therefore, at this problem from alternate or different perspectives, but all with the same aim, if we're thinking hydrology, of better forecasting on longer range timescales. Now, I mentioned, of course, that word of uncertainty, and uncertainty is sends shivers down the spines of all of us, but of course, uncertainty is inherent. It's always going to be there, whether we're talking at that from a hydrology perspective, whether we're talking at that from a meteorological parameterization perspective. So the initial conditions, how we parameterize the land surface. There's a couple of points that I've put up here, but these are, of course, just some of a wide range of uncertainties that exist in ensemble forecasting. So the uncertainty, of course, is there. The model skill, or in many cases, lack of skill, certainly as you get into longer range timescales, of course, the uncertainties and the lack of skill is very apparent. So the challenge, therefore, is how to get information from these models so they're still usable, they're still plausible, and of course can still support the use of that information. So I guess in a bit of a summary here, and I'll pick up many of these points as I go into the next half of this talk, but a summary is ensemble forecasting, whether we're talking ensemble forecasting from a meteorological perspective or from a hydrological perspective. There's a potential, and it's a growing community, is of course working between these two communities to bring meteorology and hydrology closer together, to both try and push on and extend our forecasting timescales using ensemble forecasts. So we go beyond just a week ahead, but into increasingly those sub-seasonal and interseasonal timescales. Again, of course, with that acknowledgement that ensemble-based forecasting, particularly, again, I'm talking here hydrological forecasting, we can't get too far ahead of the science. Sub-seasonal forecasts, again, they have a high degree of skill in some cases and a low level of skill in other cases and other places. So those errors and those biases and those uncertainties are very much there. But there's also the opportunity, of course, to push the science on. But it's that last point, and I was just sort of touching on that here, is for these to be successful, for that growth to come together, it's the bringing together of those two communities, but for that growth to occur, it's understanding what do we need from these? What do we need from a hydrological forecast, especially if we're talking about longer timescales? So therefore, what decisions are made on there? Who could use these and how? And of course, a bit of highlighted at the areas is how to communicate these types of forecasts, especially when we're talking about those uncertainties. So to end on this bit and to give me a nice sort of segue therefore into the next one is ensemble forecasts have an awful lot of potential, but for them to reach that potential, we need to know who to work with and how to communicate that uncertainty. And these points of co-production and working with users to reach that point of we can all understand both the uncertainties, but also the potential from these different timescales and from the use of ensemble forecasts brings me now perhaps nicely to the second part of my talk, of which this feeds into, which is around impact-based forecasting. So Impact-based forecasting, for those of us that, again, may or may not come from a communication or a forecasting side, but impact-based forecasting is the communication of information so that it provides the basis of planning and decision-making. In other words, information, can you provide something on which a decision can be made? And I've got an example there of the Stonehaven rail crash, because that's probably one of the most recent and devastating events that we've had, that is perhaps from a weather forecasting or a weather perspective, let's say. So impact-based forecasting here, if this event, well, there's an inquiry, of course, going on with this, but there's a suggestion, of course, the weather played a key role in this event. So therefore, the forecast in the event, but most importantly, the use of informationizing how a forecast can be used, will, of course, be a key discussion point within the review that takes place for the Stonehaven rail crash. So impact-based forecasting, in a very simplistic way, takes what we would call hazard forecasting. So the forecast that a flood is going to occur on a particular timescale, or the likelihood of floods going to occur on a particular timescale, and relate that to information to do with vulnerability and exposure. So it's effectively building a risk model into our understanding. So we're mixing hazard and with exposure and vulnerability, so we know the consequences. And I think it's that last word there of consequences. So if we know that something's going to happen, what are the consequences of that event happening? And this great paper here by Bruno Mertz and colleagues, which was published just a couple of months or so ago, which looks at impact forecasting around all natural hazards, so including flood in here, is well worth a look, because they do a really nice high-level summary of where the science is at across the hazards, including, like I said, including flood. So if we think of impact forecasting simply, therefore, as forecasts that lead to action, forecasts that enable us to make a decision based on the information that we are given. And of course, to do that, therefore, we need to understand all components of our forecasting chain. So from the input to the output, knowing what the impacts would likely be of this event were it to occur, and of course, other questions of where and the timing and so on. What are the limitations of that? What do our users need from this kind of information? But it's this kind of approaches that are driving our flash flood and our water, surface water flood forecast research and into operational efforts over the last few years in particular. So this example here, this is from a paper that that myself and Michael have been working with Linda Spites at Reading on. And so thank you to Linda for these couple of slides that we're showing here. So this is a paper that we've just actually, it says in mitigation, we've just had this accepted in Wires Water. This is to look at surface water flood forecasting. So although we can generalize this to be all of impact-based forecasting, I'm using surface water flooding as the example of what we're talking about here with impact-based forecasting. Now, there's a very similar looking model to the one that I showed earlier for the EFAS model, in the sense that we've got some kind of input at the beginning feeding into another model. So we're taking meteorology and feeding it into hydrology. In this case, we're feeding into a surface water flood forecasting model, from which it then needs to go into some hydrometeorological assessment, which, again, that word post-processing, so post-processing now from a hydrology perspective, and then into our warnings and action. And it's that part in particular, that inform and warn and that action part, that, of course, impact-based forecasting really sits. It's within there that we're focusing upon. And of course, if we don't have that action, then we have that feedback. And then, of course, we're looking at impact. So therefore, to know what actions to take and therefore what warnings to give, we therefore need to know what that last bit is, which is what are the impacts, which is effectively the basis, therefore, of what is impact-based forecasting. So what do we need? What do we need from a surface water or a flash flood forecast? Now, a lot of this information is based on either previous workshops. Linda was involved in a couple of series of workshops the last few years, which also again fed into work that myself and Michael and Linda did for SEPA, which was looking at preparation times and questions around timing, specific locations, how severe the impacts were going to be. So a collection here of thoughts and observations around what do our users need from impact-based forecasts in general, again, with a focus here on surface water and flash flood forecasts. The Flooding from Intense Rainfall project, which finished up in 2018, again, thank you, Linda, provided the information that fed into here, highlighted, I think, to me really clearly one of the key points that I was making with ensemble forecasting, which is for impact forecasting to be useful and to have an effect. In the same way that ensemble forecast is bringing together of meteorology and hydrology, as to our impact forecast, impact-based forecasting needs to have those two communities coming together in order to close the gap. So in ensemble forecast, I was looking at a time gap, but here we're looking at an understanding, and in particular, understanding the impacts and our users' requirements. But again, part of that gap is bringing together, or can be filled by bringing together those two communities increasingly. So although we have, of course, a lot of uncertainty around our forecasts, whether that's for, again, location, timing. We need to fill those gaps. We need to get better information and perhaps longer range information to feed into there. This is where, of course, our ensemble forecasts have a key role to play in terms of the input. And then the output side then is that impact-based forecasting side, which is more to do, of course, with the user needs and the communication side. But for that to be feasible, we of course need to know what's being done at the moment, and where perhaps we can pull on from other hazards. So examples of where impact-based forecasts are already being used or are being developed. Again, this is Bruno's and colleagues' paper that I referred to just a minute ago here, which takes a wide, high-level view across the hazards to look at where impact-based forecasts as a science are at the moment. And they're broken down into under development, or where prototypes, or where operational systems exist. And you'll see in operational terms, heat waves and earthquakes in general are sort of leading the way with operational. But it's flash flooding, pluvial, so surface water flooding, is this sort of space that the flood area are in. And in some ways we're you could say at infancy, in other cases we're at the prototype stage. So to move this onwards in terms of timescale and spread in terms of space, then it's these sort of areas that, of course, our communities are focusing on. Now, we're used to, of course, seeing our warnings, so from the Met Office and other bodies, which will forecasting centres, which will say things like, forecast of a thunderstorm, it will affect certain parts of wherever the region is, and then and an expectation of what to expect. So we're perhaps quite used to looking at these sorts of levels of data or information coming from our meteorological forecasting centres. But for this to be truly impact-based, this is very general, this is general advice, which is excellent. But for that to be more impact-based, I'm sure many of you have seen this sort of information before. This is from Mike Cranston, so thank you to Mike for this information. Again, this sort of fed into some of the work that we did with Linda towards this paper we just have produced. Now, this goes back now to the pilot surface water flood forecasting tool that was made operational during the Commonwealth Games in Glasgow. Of course, Glasgow is where I am here. Although luckily today it's not actually doing what it is in the middle day. It's not pouring with rain, but it was earlier, so that's typical Glasgow, of course. But in terms of what's plausible, what's feasible, well, we have here one of the best demonstration cases of what is possible from a surface water flood forecasting and relating that to impact. So the impact of heavy rainfall event. In this particular case, it was specific to the Commonwealth Games, but the potential and the ability to do this sort of forecasts is there. Likewise, I'm aware that SEPA, Transport Scotland, and others are starting to look at how to look at vulnerable parts of the transport network. This is from Michael Cranston's blog on the Scottish Flood Forecasting Service, starting to look at examples of more impact-based forecasting, and again, where the potential of that can lie. So from a feasibility perspective, we're very much we're heading towards that sort of direction. But which approach do we take? In which direction do we need to be spending, I guess, our time and our efforts? And a lot of this is going to depend on, again, our users, our communication, knowing what levels of risk they're willing to accept versus the cost and the outlay to understand what those impacts are and what they may mean, and actions to reduce those impacts were an event to happen. So of course, that's the key routine, I suppose, for forecasts, is to put all this together to build a decision-based, impact-based forecasting tool. Now, in the final piece here, I just want to focus on, again, on surface water flood forecasting. We can generalize this for all impact forecasting, but the work that I did with Linda and Mike was to do a review of surface water flood forecasting for SEPA. This was produced just earlier this year. And in there, we look at all the components that make up a surface water flood forecast model. And in particular, we're looking at it from a forecasting perspective, an impact-based forecasting perspective. And we kind of summarize, so this was a bit of a benchmarking exercise. It was to see where SEPA's capability is at the moment, how that matches up, therefore, against others internationally, and therefore, of course, some future directions. Where do we need to go with surface water flood forecasting? And therefore, impact-based forecasting in more general, which is, I guess, the message I'm trying to pull from this. So from this, we focus on three areas: empirical-based scenarios, hydrological forecasting linked to pre-simulated scenarios, and then very much at the urban scale, so linking of hydrodynamic models at the urban scale, all fed by hydrological forecasts in the first, as the driver, as the input. Now, in this paper, we explore those three areas in turn. And again, this is perhaps where the potential for ensemble forecasts very much have probably a key role to play, certainly in the development of these as we move forward. The input into empirical-based rainfall scenarios, so that's again, that's sort of relating it back to known thresholds and known values. Typically, that'll be input by numerical weather forecasts. But as we're looking to either to reduce uncertainty and or to push that into other forecasting timescales, then it's ensemble forecasts as the input to the comparison against these empirical-based thresholds and scenarios that will enable flood forecasts to be produced. This is one of those kind of three spaces where there's potential there for growth. And in each of these three cases, we've got some examples, advantages and disadvantages related to each of those. Similarly, for the second of those three pieces, pre-simulated impact scenarios, again, this is very dependent here on those ensembles feeding into a real-time hydrological model based against more of a static map-based scenario to produce something that talks to impacts at the end. So again, same different pathway, but always trying to get to this point here of impact. And again, here we tried to pull together some of those operational examples. This is where the Glasgow surface water flood forecasting pilot project from the Commonwealth Games comes in. And then lastly is to the third component, which is more around the now casting, I suppose, timescale, which would be to link more the shorter range forecasting rainfall, feeding that into a model to get urban scale, so very localized, very specific impacts from models, and I would probably say that this is very much at the cutting edge. This is very much the emerging area of science when it comes to hydrological forecasting, which very neatly sort of blends together the want for both better forecasts, ensemble forecasts probably, as well as, of course, the better understanding of impacts and impact forecasting. So again, a bit of a summary for that sort of second part here really is not dissimilar in many ways to the ensemble forecasting. In that it's the bringing together of different communities, it's the bringing together of understanding different disciplines. In this case, we're bringing together risk and impact, so exposure, vulnerability information, and matching that or marrying that up with better forecasts, but of course, as well as encapsulating the predictability, but as well, but with that, the uncertainty, of course, as well. So it's bringing together these threads, these different disciplines to try and, of course, get to something that produce better models and better forecasts that are then usable. So I'm sort of at the end here of my talk. I'm just a couple of minutes over. I'll leave with just some concluding remarks, which you can probably sort of gauge what they'll be, probably from the flavor of the talk that I've got there. But again, it's just around those points of bringing together those communities, advances in models, whether that's convection permitting numerical weather prediction to improve those nowcasting models, or so really being, I guess, pointing towards more here is those ensemble forecasts to produce those longer range stream flows, and the matching that up with impact-based forecasting. Okay, I'll stop talking there. Of course, happy to take some questions. I'll stop sharing my screen just so you're not just looking at that, and I'll end there. Thank you very much.
Thank you, Chris. That was a really, really great overview of hydrological forecasting. And I think we've got some questions already come in on the chat. So I'll just bring those up. I think the first question was from Keith Evan. So Keith, if you'd like to unmute your microphone, I'll let you ask your question.
Hopefully you can hear me now.
Yes, yes, great.
I was really wanted to raise the issue about the type of forecasting that Christopher's mostly been talking about, which is aimed at more longer term warning situations, and the real-time flood forecasting that you might do in operational senses for individual events, because to my mind, at least, the techniques required are rather different. There is a whole range of scales for which you don't need ensemble NWP inputs. In fact, they might be, in terms of my experience of trying to use NWP for real-time forecasting, it might be actually disadvantageous. But at smaller scales, where the time lags are too small, you need some prediction of rainfalls. And at the longer time scales, then beyond the time lag of the system, then you might, you also need some inputs of rainfalls. But there's a type of scale in the middle where perhaps the most important aspect is the adaptation, the real-time adaptation of the forecast, because we can be pretty sure that our estimates of rainfall going in are not going to be necessarily good. So you don't necessarily want to use a model a hydrological model that maintains mass balance, for example. You would want to have that adaptive so that you can correct for the errors in the rainfalls. And there's a point there in relation to NWP precipitation forecasts, in that the ensemble is not produced with a view to getting the statistics of the rainfalls right. It's produced for quite other reasons. It gives you a range of uncertainties, but they're not necessarily linked to the any expectation of probabilities in rainfall ranges. So I did suggest in the question, do we actually need different names for the two different types of forecasting? Or do we call it all forecasting and try to differentiate between that?
Mm.
Any comments from Chris on that would be very useful.
Yeah, it's a very, thank you, Keith. It's a very, very interesting, interesting question, because forecasting, having come from a hydrological background, then sort of dipped my toe as a meteorologist for a few years, and then come back to hydrology more. Forecasting, I tend to think of more from a deterministic perspective. The word forecasting, that is, so an event will happen on a particular day, or the likelihood is it will happen on a particular day in a particular place. Having worked on ensemble forecasting for a number of years, the word that often gets used to, and the sub-seasonal, interseasonal, so those longer range timescales, forecasting actually is often replaced with prediction or outlook. Especially if you get to the seasonal timescale, we're talking outlook at that point, because we're talking week or fortnight averages at best, not specifics. We're not talking about specific days or times. So you're absolutely right. I'm blending a little bit there, forecasting in a very general sense to mean, because a seasonal outlook is still a forecast. It's just not it doesn't have that time or date precision to it. But I think in terminology, you're absolutely right. Forecast, I think, should potentially, and perhaps it mainly is used for an event, so the likelihood of an event occurring, and prediction or outlook, or another term that encompasses those sort of points, is more around the likelihood of a type of an event, or an increased likelihood of, let's say, heavy rainfall or a flood occurring, which can then potentially, as we get to those nearer timescales, can then be replaced with a more precise deterministic forecast.
Yeah, and I think a particular role here has to play with the possibility for hydrological adaptation. If you can feed back water levels or into the forecast, I think within the lag time of the catchment area to the flood risk area that you're interested in, then that's really important. But as I said earlier, that's very difficult when the lag times are very short, and it's very difficult when the lag times are quite long. So it is this range of scales, I think, that perhaps needs to be brought out, and where different techniques might be useful.
I think so, yes. And I think as well, part of the challenge, but also part of the opportunity of very much bringing together meteorological and hydrological communities, I think in many ways has the potential to address those kind of questions, I think, because probably I'm generalizing, of course, but everyone will have their own sort of take on what a forecast is, what sort of timescales we're perhaps all used to dealing with. But bringing together those two communities, I think, has a lot of potential, I think, in there.
Great, thank you for that. We've got a question from James. I'm not sure he's still on the call, but their question is, end users often experience impacts very locally. What drives how local a model needs to be useful?
It's a very good question, and one that would be very dependent on the user, as in the person or the system or the piece of infrastructure or the decision maker, would be based upon. So if we're talking surface water flood forecasting, any flood forecast, I suppose, whether it's flash flood or surface flood forecasting, how local is local enough? It's when it's informative enough on which you can make a decision. Now, that's a really vague answer, I know, but ultimately it's what information do you need that would make you either change or not your choice of staying somewhere, evacuating, or running a train down a train line or not, closing a road or not. It would depend very much on whether you're talking urban or rural landscapes as well. So it depends on what is being impacted. And I think that what you're probably really highlighting is one of the real challenges around impact-based forecasting, irrespective of timescale, is understanding people's and systems' exposure and vulnerability, because everyone and everything is different. And if you know what that information is, then I think you can then work backwards to say, how local does a model need to be? How precise, how general, at the other end of the scale, does that model and does that approach need to be? So I think there isn't an answer necessary to it. But I think you've very much highlighted, I think, one of the key challenges there that comes with impact-based forecasting.
Perfect. Thank you. We have a question from Jane, so I invite Jane to ask her question to you, if you're able, or I can read it out.
Hello, can you hear me?
Yes.
Yes.
Yeah. I'm a water resources hydrologist. Unfortunately, as far as I was concerned, this was all based on flood forecasting. Just wondered whether these methodologies could be used for drought forecasting and the impacts for water resources.
Well, from an ensemble forecasting perspective, so talking more perhaps from a meteorological, longer range forecasting meteorological perspective, because subseasonal and interseasonal predictions, let's move away from the word of forecasting, they naturally lend themselves to more slowly developing, longer lasting events or hazards. If we're talking drought here, the drought, it very much sits within something that might happen over weeks, months, potentially even years for a drought. So a probabilistic longer range forecast, because of the uncertainty, but because of perhaps the spread of the impacts of drought as well. So we're going from perhaps localized in a flood sense, but when you're talking drought, you're often talking much more wide space. I would say the potential actually for the use of, say, longer range and ensemble, meteorological ensemble forecasts is much greater in some ways for something like drought, in the same way it would be perhaps for heat wave forecasting, moving out of the hydrology space, because of the phenomena and the way that the spatial and temporal components. Flood forecasting in comparison, therefore, is probably one of the biggest challenges, because of the typically more localized and quicker occurring events, based primarily, of course, on local rainfall events. So actually what we're talking about here is, in flood forecasting, is probably a bigger challenge than, say, drought, and therefore water resource forecasting, than I think what you're asking about there, Jane.
Thank you, Chris.
Great. Well, we are at 2 o'clock, so I think we'll leave it there for today. And thank you again, Chris, for your fantastic presentation.
Thank you.
I think that was really, really great. And there's been a few questions around whether the slides will be available. There will certainly be the recording available on the BHS YouTube channel, which should go up hopefully this week or very soon. So you should be able to rewatch it there. And we may be able to, in discussions with Chris, make slides available if that's appropriate. So watch out for those. Our next lunchtime webinar is on the 25th of November, and that will be given by our President-elect, Hayley Fowler, on anthropogenic intensification of short duration rainfall extremes. And that will be at a slightly later time, 2 till 3. So you can look out for registration for that webinar coming out soon, and we hope to see you there. And thank you again, Chris, for that fantastic talk today.
Thank you very much for having me, and thanks to everyone for attending and sticking with me through your lunch hour. And yeah, I'll send the slides through, and if anyone wants to contact me independently to ask for slides, I'm of course happy to share those. Thank you.
Fantastic. Thank you again. Thanks, everyone.